The sun rises slowly over North America. It begins in the east, somewhere above the cold Atlantic waters, where the first pale light touches the outer edge of the continent like a hand gently resting on a sleeping shoulder. The light moves inland. It crosses the rocky headlands of Newfoundland, drifts over the spruce forests of Maine, and begins its long, patient journey westward across a continent so vast that even the dawn itself takes hours to complete the crossing. If you could follow that light from above, rising high enough to see the whole land at once, the view would take the breath away quietly, the way beautiful things sometimes do, without drama, without announcement. Before we go any further, if you are settling in for this journey tonight, we would love for you to take just a moment to like this video and subscribe to History Sleepy Time so that you never miss a new documentary. And leave us a comment. Let us know where in the world you are watching from tonight. It is always a quiet pleasure to know where our listeners are resting. Now, let us descend. Below you, mountains rise in long, dark ridges. The Appalachians stretch from the Canadian Maritimes all the way down toward Alabama, their ancient rounded peaks softened by hundreds of millions of years of wind and rain, their slopes thick with hardwood forests that turn gold and amber in the autumn light. These are old mountains, patient mountains. Mountains that have been standing so long they have forgotten the urgency of height. The light continues west. The great river systems of the interior begin to shimmer in the early morning. The Ohio, the Cumberland, the Tennessee, all of them feeding southward into the Mississippi, which carries the continent's rainfall in a slow brown procession toward the Gulf of Mexico. You could watch those rivers for a long time and feel very still, the way rivers make people feel still. Farther west, the forests thin and open into grassland. The Great Plains unfold beneath you like a page waiting to be written on, enormous, quiet, golden in the morning light, stretching from the Dakotas down through Kansas and Oklahoma and into the vast flatlands of Texas. Somewhere in that immensity, a hawk is circling. A herd of pronghorn antelope moves slowly through the grass. The wind bends the bluestem in long, slow waves, and then the land begins to rise again. The front range of the Rockies appears on the western horizon, and the mountains that come next are younger, sharper, more dramatic than the Appalachians, the kind of mountains that seem to be reaching for something. The Rockies give way to the Colorado Plateau, with its red canyon country and its mesas standing like monuments to time itself. The desert southwest stretches out in shades of ochre and rust and pale sand, marked here and there by the dark green lines of riparian corridors where water still runs. The Great Basin lies beyond, ancient and dry and enormous. And finally, the Sierra Nevada and the Cascades rise to meet the Pacific, where the continent ends in cliffs and tide pools and the smell of salt. This is North America at dawn, mountains and forests, rivers and deserts, grasslands and canyons. Ice fields in the north, subtropical wetlands in the south. A continent of astonishing variety, astonishing scale, and astonishing beauty. And yet, there is something the dawn light cannot reach. Something that has been present beneath every one of those landscapes, beneath the Appalachians and the Rockies, beneath the Great Plains and the Ozark Hills, beneath the Mojave Desert and the Cumberland Plateau. something that has existed for millions of years in complete and unbroken darkness. Beneath this continent lies another world, not a world of darkness in any frightening sense, but a world of extraordinary stillness. A world of ancient stone and slow water, of crystal and silence, of passages that stretch for miles without a single breath of surface wind ever having touched them. A world that was old before the first trees grew on land, old before the first fish swam in shallow coastal seas, old in the way that only geology can be old, measured not in decades or centuries, but in epochs, in the slow turning of the earth itself. North America contains hundreds of thousands of known caves, hundreds of thousands, and those are only the ones that have been found. Geologists and speleologists, the scientists who study caves, estimate that the known cave systems of this continent represent a small fraction of what actually exists beneath the surface. Some cave regions have been surveyed in detail. Others have barely been touched. Vast areas of karst landscape, the type of geology most likely to produce cave systems, remain almost completely unexplored at depth. The question that sits at the heart of this documentary is one that geologists and cave explorers have been asking for decades, and it is a question that grows more fascinating the longer you sit with it. Could the greatest wilderness in North America lie not above the ground, but quietly beneath it, not the wilderness of mountain ranges or old-growth forests, not the wilderness of Arctic tundra or Sonoran desert, but a wilderness of stone and water and darkness, a wilderness that has never seen sunlight, that has never felt the movement of wind, that exists in a silence so complete it has its own particular quality, its own particular weight. There are cave passages in North America that extend for miles and have never been entered by a human being. There are underground rivers that have flowed in complete darkness for thousands of years without ever being observed. There are chambers so large that clouds have been known to form inside them, actual clouds, mist rising from underground lakes to collect against the stone ceiling far above. There are formations so delicate that a single breath would destroy centuries of growth. There are ecosystems so isolated that the creatures living within them have evolved entirely independently of the surface world, developing over millions of years into forms found nowhere else on Earth. And there are passages, long, winding, water-carved passages that nobody has yet followed to their end. This is the story of North America's underground world. It is a story told in limestone and water, in geological time and human curiosity, in the patient accumulation of knowledge over centuries of exploration. It is a story without a final chapter because the exploration is still ongoing. It begins, as most deep stories begin, with the land itself, with the ancient processes that built the hidden world beneath our feet. So now let us follow the light down past the soil, past the roots of the oldest trees, past the first layers of bedrock, down into the cool and ancient dark where the continent keeps its oldest secrets. The surface fades, the sound of the wind fades with it, and the stone closes quietly around us. To understand the caves beneath North America, you have to travel back in time, not years or decades or even centuries, but hundreds of millions of years. You have to go back to a world that would look almost unrecognizable from the surface of today's continent begin roughly 500 million years ago. The world is warmer then. The continents are arranged very differently than they are now, and the landmass that will eventually become North America sits partly submerged beneath a shallow inland sea. A warm, sunlit, tropical sea that stretched across much of what is now the central and eastern part of the continent. This was not the deep ocean. It was shallow enough for light to reach the bottom, warm enough to sustain enormous communities of marine life, corals and crinids, brachiopods and mollusks, the tiny calcite-shelled organisms that lived and died in their billions and sank slowly to the seafloor when their brief lives were over. This went on for an almost incomprehensibly long time. For hundreds of millions of years, those shallow seas persisted, shifting and retreating and returning, covering different parts of the continent at different times, and with every cycle, more marine organisms lived and died and settled to the bottom. Over time, geological time, which is to say time measured in millions of years, those accumulated remains were compressed by the weight of sediment above them. The soft, organic material dissolved away. What remained was calcium carbonate, the mineral building block of bone and shell, compressed and recrystallized over millions of years into the pale, dense, slightly alkaline rock we call limestone. Limestone is, in a very real sense, a graveyard. Every square foot of it contains the compressed remains of creatures that lived and died in ancient shallow seas. The great limestone formations of Kentucky and Tennessee, of Missouri and Arkansas, of Texas and New Mexico, all of them began as living communities on the floors of warm interior seas that no longer exist. In some parts of North America, the limestone formations are thousands of feet thick. In Kentucky, the limestone bedrock that underlies the famous cave country extends to depths of several hundred feet in some areas, and has been accumulating since the Ordovician period, roughly 450 million years ago. This is stone that was already ancient when the dinosaurs were young. Alongside limestone, another rock called dolomite plays an important role in the underground story. Dolomite is chemically similar to limestone, but contains magnesium as well as calcium carbonate. It forms through a process of chemical alteration of magnesium-rich water, gradually replacing some of the calcium in limestone formations over time. Dolomite is slightly harder and less reactive than limestone, but under the right conditions, it too can be dissolved and shaped by moving water. Many of the cave systems of the Ozarks and the Great Lakes region have formed partly within dolomite formations. But the story does not end with the rock being created. Once the seas withdrew, as they did repeatedly over geological time, and once the land was lifted above sea level by the slow grinding forces of continental tectonics, the limestone was exposed to a new and very patient sculptor: rainwater. Here is something that seems simple but has profound consequences. Rainwater, as it falls through the atmosphere, absorbs small amounts of carbon dioxide from the air. When that slightly acidic water, what geologists call carbonic acid, though in the concentrations found in rainwater it is very weak, comes into contact with limestone, it begins very slowly to dissolve the rock. not quickly, not dramatically. A single raindrop falling on a limestone surface does essentially nothing perceptible. But over thousands of years, over hundreds of thousands of years, the cumulative effect of rainwater moving through cracks and fractures in limestone rock is enormous. The acid dissolves the calcium carbonate, carrying it away in solution. The cracks widen, the fractures become channels, the channels become passages, the passages eventually become caves. This process is called karstification, and the landscapes it produces are called karst, a word borrowed from the karst region of Slovenia and Croatia, where this type of terrain was first extensively studied by European geographers. Karst landscapes have a distinctive look at the surface. In well-developed karst country, you will find gently rolling terrain pocked with circular depressions called sinkholes, where the ground has subsided into dissolving rock beneath. Springs emerge from hillsides where underground rivers reach the surface. Small streams disappear suddenly into the ground at points called swallow holes or swallets, vanishing into the underground drainage system below. The topography has a subtly dimpled, irregular quality that reflects the hollow architecture beneath. In North America, karst landscapes underlie enormous areas of the continent. The interior low plateaus of Kentucky, Tennessee, and Indiana are underlain by some of the thickest and most cave-productive limestone formations in the world. The Ozark Plateau of Missouri and Arkansas sits atop a vast dome of ancient limestone and dolomite that has produced thousands of caves. The Guadalupe Mountains of New Mexico and West Texas contain cave-forming limestone of a completely different geological origin. These caves, unlike most, were formed not by descending rainwater, but by sulfuric acid rising from below, a process called hypogenic or sulfuric acid speleogenesis. The Black Hills of South Dakota contain cave systems formed in Mississippian limestone. The Appalachian Valley and Ridge Province contains numerous cave systems in folded and faulted limestone and dolomite formations, and across large areas of the American West. Ancient lava flows have produced a completely different type of cave, lava tubes formed not by chemical dissolution, but by the physical process of flowing lava cooling and hardening on the outside, while the molten interior drains away, leaving hollow tunnels, sometimes miles in length. Each region has its own geological story. Each has its own timetable. The caves of the Guadalupe Mountains, for example, formed within the last 12 million years through processes still not fully understood in all their details. The caves of the Mammoth Cave region of Kentucky have been developing for at least 1 million years, and possibly longer. The lava tubes of the Pacific Northwest and the Southwest are much younger, some only a few thousand years old. But across all of these different geological settings, the underlying principle is the same. The rock was laid down by ancient processes. Time passed, enormous quantities of time. Water found the weaknesses in the stone, and slowly, molecule by molecule, the rock gave way and passages formed. And those passages grew, and eventually, they connected to other passages and systems developed that are so large and so complex that even today, with all of our technology and all of our accumulated knowledge, we cannot fully map them. Continental uplift played a crucial role in this story as well. As the land rose, driven by the slow collision and movement of tectonic plates, the water table dropped in many regions, leaving previously water-filled cave passages drained and open to air. These air-filled passages are where most of the formations that people associate with caves, the stalactites and stalagmites, the flowstone and the cave pearls, the delicate helictites and crystal formations, began to grow, where the cave is above the water table. Water seeping through the rock above carries dissolved calcium carbonate into the passage, and as it drips from the ceiling or flows across the floor, the carbon dioxide escapes into the cave air. And the calcium carbonate is deposited, one infinitely thin layer at a time, building formations of extraordinary beauty over thousands of years. A stalactite 1 foot long may represent many thousands of years of growth. The cave is always growing, always changing, always building itself, but on a timescale so slow that a human lifetime is not even a rounding error in the calculation. This is what lies beneath North America, not simply holes in the ground. Not simply dark spaces where the rock is missing, but an architecture of astonishing complexity and beauty, built by the patient cooperation of chemistry and time, of water and gravity, and the slow movement of the continent itself. A world that began forming before the first forests appeared on land. And that continues forming today, this very night, as water drips from cave ceilings in the darkness, and another infinitesimal layer of calcite is deposited on a formation that will outlast every living thing now on the surface of this planet. The rock built the labyrinth. Now let us follow the water that gave it life. There is a river flowing somewhere beneath your feet tonight, not necessarily immediately beneath you, but somewhere beneath the ground you stand on, beneath the roads and the fields and the parking lots and the forests. Water is moving. It has been moving for a very long time. It follows paths established over thousands of years, flowing through passages in the rock that no human eye has ever seen, carrying dissolved minerals from one place to another, building cave formations in one location while slowly enlarging passages in another. The underground hydrological systems of North America are among the most complex and least understood natural systems on the continent. They connect the surface world to the underground world in ways that took scientists a very long time to begin to understand, and that are still not fully mapped in most regions. The story of underground water begins at the surface with rain. When rain falls on karst terrain, some of it runs off across the surface in streams and rivers, but a significant portion seeps into the ground. It moves down through the soil, through the fractured rock, through joints and bedding planes in the limestone, slowly, patiently, following gravity and the path of least resistance. Some of this water enters caves directly through sinkholes or swallow holes. Some enters through the microscopic pore spaces in the rock itself. As this water moves downward, it is doing two things simultaneously. It is being shaped by the rock, following the passages and cracks that already exist. And it is shaping the rock, slowly dissolving limestone and enlarging the passages it flows through. Eventually, descending water reaches the zone of saturation, the level below which all the pore spaces and fractures in the rock are completely filled with water. This is what we call the water table, and the saturated zone below it is what we call an aquifer. Aquifers are not underground lakes in the popular imagination. They are not great open bodies of water in dark caverns. In most cases, they are masses of saturated rock, where water fills every available space. But in karst terrain, where the rock has been dissolved into a complex network of passages and chambers. The aquifer can indeed include open cave passages entirely filled with water, what cave divers call sumps or phreatic passages, as well as streams and rivers flowing through air-filled cave passages above the main water table. The underground rivers of North America are extraordinary. In the Mammoth Cave region of Kentucky, the cave system is drained by several underground rivers that flow through its lowest levels. These rivers collect water from the land surface above through hundreds of sinkholes and sinking streams, carry it through miles of underground passages, and eventually discharge it into the Green River, which flows through the valley below the cave plateau. The relationship between the surface drainage and the underground drainage in this region has been studied for more than a century, and scientists are still working out its full complexity. One of the most powerful tools for understanding underground water flow is a technique called dye tracing. Hydrologists introduce a non-toxic fluorescent dye, typically one called fluorescein, which is brilliant green, into a sinking stream or a sinkhole. Then they place passive detectors in springs and streams in the surrounding area. When the dye appears at a particular spring, it demonstrates a direct hydrological connection between the point of introduction and the spring, and it gives scientists information about the speed of flow, which can help them understand the nature of the conduits the water is moving through. Dye tracing results in karst areas are frequently surprising. Water that enters the ground at one point may travel for miles underground and emerge at a spring in a location that seemed, from the surface topography, to be completely unrelated. Underground drainage divides the boundaries between different underground drainage basins, often bear no relationship at all to the surface topography. A farmer's well on one side of a gentle surface ridge might be in an entirely different underground drainage basin than a well 200 yards away on the other side. This matters not just scientifically, but practically. Karst aquifers are extremely vulnerable to contamination. Because pollutants that enter the ground through sinkholes or sinking streams can travel very rapidly in some cases. At speeds of several miles per day through large cave conduits, to springs that may be miles away and that may be providing drinking water for communities that have no idea the hydrological connection exists. The underground rivers of the Ozarks are among the most extensively studied in North America. The region's vast limestone and dolomite formations, gently domed by ancient geological uplift, are dissected by underground drainage systems that have been developing for millions of years. Big Spring in Missouri, one of the largest springs in the United States, discharges an average of around 280 million gallons of water per day. This water has traveled underground through a complex network of cave passages from points of entry many miles away, and the full extent of the cave system feeding it has never been completely mapped. In the Edwards Plateau of Texas, The Edwards Aquifer is one of the most productive karst aquifers in the world. It provides water for the city of San Antonio and surrounding communities, water that enters the aquifer through losing streams in the recharge zone to the north and west, flows through cave passages in the limestone, and emerges in major springs along the Balcones escarpment to the south. Comal Springs and San Marcos Springs, which discharge from this aquifer, are among the largest springs in the American Southwest and sustain ecosystems of remarkable biological richness, including several species found nowhere else on Earth. The connection between surface water and underground water in karst terrain creates cave systems in a particular way. The cave passages that carry underground streams tend to develop along the path of maximum hydraulic efficiency, the route that allows water to move most easily from its point of entry to its point of discharge at a spring. Over time, the most efficient passages carry the most water and are enlarged the fastest. Less efficient routes receive less flow and enlarge more slowly. The result is a cave system that is not a random tangle of passages, but an organized, hierarchical drainage network, just like a surface river system, but hidden in the rock. Cave streams can be powerful things. In flood conditions, an underground river can carry enormous volumes of water moving with considerable speed through passages that are completely filled from floor to ceiling. This flood pulse erosion is responsible for much of the largest cave passage development. The great horizontal trunk passages of Mammoth Cave, some of them 50 feet wide and 30 feet tall, were carved by rivers flowing under flood conditions during periods of higher water table thousands of years ago. As the water table drops over geological time due to valley deepening and regional uplift, the cave develops in a particular pattern. Upper levels that were once underwater passages become air-filled, and the active stream finds its way to lower elevations, carving new passages as the old ones become dry and decorated with formations. The multi-level architecture of a cave like Mammoth, with its upper dry fossil passages and its lower active stream passages, is a record of this history written in stone. And everywhere in these dark passages, water is working. Even in the dry upper levels, water seeps through from above. It trickles along the ceiling, collects on the tips of growing stalactites, falls in slow drops to the floor. It moves invisibly through the rock in thin films, depositing infinitesimal quantities of calcium carbonate with every passing hour. The cave is never truly still. It breathes with the seasons. A cave air circulation changes as temperature differentials between the cave and the surface shift, and it responds to rainfall events that may have happened miles away and weeks ago. There is a profound slowness to all of this that is worth sitting with for a moment. The underground rivers of North America did not appear overnight. They are the product of millions of years of gradual, patient work. A passage that is now large enough for a person to walk through may have begun as a crack in the rock, no wider than a hair. Widening that crack to its current size took, in many cases, hundreds of thousands of years. This is perhaps one of the most humbling aspects of the underground world. When you stand in a cave passage and look at the walls around you, you are looking at the accumulated work of geological time. Time so vast it cannot really be held in the human mind, only gestured at. The passage you are standing in was being carved when your ancestors' ancestors had not yet appeared on this continent. It will still be there, still slowly changing, still dripping and depositing and dissolving, long after every trace of human civilization has been erased from the surface above. The underground rivers of North America connected the great cave systems we will explore in this documentary. They are the arteries of a living geological body. And understanding them, understanding how they flow, where they go, how they respond to rainfall and drought, is one of the central scientific tasks of modern cave research. Some of the greatest questions in North American hydrogeology remain unanswered. How far do certain underground drainage systems extend? How many cave passages remain full of water, permanently flooded, accessible only to cave divers with specialized equipment? And how large are they? What is the total volume of water stored in North America's karst aquifers, and how is that volume changing as climate shifts? These are not merely academic questions. The aquifers that feed springs across the American South and Midwest and West are sources of drinking water, agricultural water, and ecological sustenance for millions of people and countless species. Understanding them is a matter of genuine practical importance. But it is also simply wonderful in the old sense of that word, full of wonder, to contemplate the rivers that flow beneath the continent unseen and unhurried, carrying the continent's rainfall through stone corridors that no sunlight has ever touched. On their long journey toward the springs, where they will finally emerge blinking into daylight after their long passage through the dark. Those rivers have been flowing since before the first humans set foot on this continent. Which brings us to a different kind of question, not the geological question of how the caves formed, but the human question of what happened when the first people arrived and found these places waiting in the earth. Imagine standing at the edge of a cave entrance somewhere in what is now Tennessee or Kentucky or Alabama, roughly 4,000 years ago. The morning air is cool. The forest around you is dense and old, white oak and tulip poplar, hickory and beech, their canopy so thick that the light falls through it in scattered pieces, dappled and shifting. The entrance to the cave before you is a dark opening in a limestone bluff, perhaps 8 or 10 feet across, framed by ferns and the pale roots of trees that have grown over the lip of the stone. A breath of cool air moves outward from the darkness, the cave exhaling, as caves do, when the outside temperature is warmer than the air within. You are not the first person to stand here. The evidence of earlier presence is all around you if you know how to read it. The soil near the entrance has been disturbed by years of foot traffic. The limestone walls just inside the entrance are stained with the carbon of old fires, and somewhere deeper in the darkness, in passages that require a torch to navigate, the traces of human presence go back much further than the evidence at the entrance suggests, back to a time so distant that the people who left those traces behind lived in a world that would look very different from this one. The archaeology of North American caves is one of the richest and most carefully studied fields in American science. and what it reveals consistently and across a very wide geographic area is that human beings have been entering the caves of this continent for a very long time, not simply sheltering at their entrances, but venturing deep into their interiors, navigating passages of considerable length and difficulty, and leaving behind evidence of activities that range from the practical to what appears to be the ceremonial. The oldest confirmed evidence of deep cave exploration by human beings in North America comes from a region of the American Southeast, particularly from cave systems in Tennessee, Alabama, and Kentucky. Archaeological research in these caves, careful, methodical research conducted by professional archaeologists over decades, has documented human presence in the deepest parts of cave systems that dates back at least 4,000 years, and in some cases considerably longer. Among the most remarkable categories of evidence are ancient footprints. In several caves in the American Southeast, researchers have documented the preserved footprints of people who walked through soft, cave mud thousands of years ago. The mud dried or was covered by later deposits, and the impressions survived. These are not vague impressions or ambiguous marks. They are recognizable human footprints, the heel, the arch, the toes, frozen in the stone of geological record. In one documented case in a cave in Alabama, a set of footprints appears to represent a small group of people, including at least one child, who walked together into the darkness on some errand that we can no longer fully reconstruct. The footprints go deep into the cave, away from any natural light, away from any entrance, into the kind of darkness that, without an artificial light source, is absolute. These people carried torches. The evidence of ancient lighting is another remarkable category of cave archaeology. In numerous caves across the Southeast, archaeologists have recovered fragments of cane torches, sections of river cane that were bundled together and burned as a light source. River cane burns steadily and produces a clear, warm light adequate for navigating cave passages. The cane fragments found in these caves have been radiocarbon dated, and the dates cluster in a range from roughly 3,000 to 4,000 years before the present, placing these explorations in what archaeologists call the woodland and archaic periods of North American prehistory. The preservation of these organic materials is itself remarkable. Caves, with their stable temperatures and humidity, their darkness, and their relative isolation from the biological processes that decompose organic matter on the surface, can preserve fragile materials for extraordinary lengths of time. In some caves, the conditions are dry enough that organic materials have survived for thousands of years in near-perfect condition, a fact that has made caves among the most valuable archaeological sites on the continent. Beyond the torches and the footprints, the evidence of deep cave activity includes a remarkable range of artifacts and features. Gypsum is a soft mineral, calcium sulfate, that forms in many caves as water evaporates from solution and deposits its dissolved load on the cave walls and floors. Gypsum can accumulate in beautiful formations, flowers, needles, curved sheets, and it can also accumulate in thick deposits on cave floors. In several caves in the Southeast, archaeologists have documented evidence of ancient gypsum mining. People entered the caves, broke gypsum from the walls or collected it from the floor, and carried it out. The uses of gypsum in prehistoric contexts are not fully understood. It may have been used as a pigment, as a medicine, or for other purposes, but the activity itself is well documented, and the evidence suggests that it was conducted systematically, not incidentally. Ancient fires have been documented deep inside caves far beyond the reach of natural light. These are not campfires at the cave entrance. They are fires built in the interior, sometimes in locations that seem carefully chosen, in chambers of particular acoustic quality, or at the base of features that may have held cultural significance for the people who built them. The carbon from these ancient fires, analyzed with modern techniques, provides dates that extend back thousands of years. Rock shelters, shallow overhangs of limestone, where the rock has weathered back to create a natural roof, but where there is no deep cave behind, were used extensively as habitation sites across the karst regions of eastern North America. These sites are among the richest and most carefully studied archaeological sites on the continent. The rock shelter at Dust Cave in Alabama, for example, preserves an archaeological sequence spanning thousands of years of human occupation, and the material recovered from it has contributed enormously to our understanding of early prehistoric life in the region. Cave burials represent another important category of evidence. In several cave systems in the American Southeast and Midwest, the remains of people who were deliberately placed in cave passages or chambers have been found. These burials are treated with great care and sensitivity by archaeological researchers, in coordination with the descendant communities who have cultural and spiritual connections to these individuals. The presence of burial practices in caves is significant not simply as a data point about ancient behavior, but as evidence that caves held a place of cultural and perhaps spiritual importance for the people who used them, important enough that these were chosen as places to lay the dead. The picture that emerges from decades of careful archaeological work is one of a sustained, purposeful human engagement with the underground world that goes back thousands of years. The people who entered these caves were not stumbling into them by accident. They were making deliberate choices, equipping themselves with light sources, navigating complex passage systems, conducting specific activities, and returning to the surface. They were, in the most literal sense, cave explorers. And they were exploring some of the same cave systems that professional speleologists are still working to map and understand today. The caves of the Cumberland Plateau, the caves of the Ozarks, the caves of the Guadalupe Mountains. These places were known to human beings long before the arrival of European settlers, long before the development of modern speleology, long before the invention of nylon rope and electric headlamps and satellite-connected GPS devices. The first explorers of North America's underground world were Paleo-Indian and archaic and woodland period peoples, who carried bundled cane torches into passages of darkness and found their way back to the light. What exactly motivated them, what drew them into the darkness, what they were seeking, what they found, is something that the archaeological record can only partially address. Archaeology tells us what people did. It tells us where they went and what they left behind. But the inner life, the meaning that people attached to their experiences in the underground world, is something that lives in cultural memory, in tradition, in the living knowledge of descendant communities. And that brings us to a chapter of this story that deserves its own careful, respectful consideration. Because the indigenous peoples of North America did not simply visit caves and leave them behind. Many nations developed sustained and complex relationships with the underground world, relationships that were spiritual and ecological and cultural all at once, relationships that have been maintained across generations and that continue in some form to the present day. These are not stories that archaeology can fully tell. They are stories that belong to the nations themselves. Before we go any further into this chapter, it is important to say something clearly and simply. North America is not a single cultural landscape. It is not one story. The continent was home, at the time of European contact, to hundreds of distinct indigenous nations, each with its own language, its own governance, its own history, its own relationship to the land, and its own body of knowledge about the places where that people lived. These nations were as different from one another as the nations of Europe are different from one another, and in many cases more so. To speak of what indigenous peoples believed about caves, as if there were one unified indigenous relationship with the underground world, would be a distortion, a flattening of extraordinary diversity into a false simplicity. It would do a disservice to every nation involved. What can be said, honestly and with care, is this. Across many different parts of the continent, and among many different indigenous nations, caves and springs and underground water sources held significance that went beyond the purely practical. The specific nature of that significance varied enormously from nation to nation, and the traditions that express it belong to those nations and are properly understood through their own frameworks, not translated into a single generic narrative. With that said, and with great care to distinguish between what different nations have shared publicly about their own traditions, let us consider some of the ways in which specific indigenous nations of North America have related to the underground world. Among the Cherokee people, whose traditional homeland encompassed much of the southern Appalachian Mountains and the plateau regions of Tennessee, Georgia, and the Carolinas, caves appear in recorded oral traditions in ways that reflect a complex understanding of the underground landscape as part of a larger ordered world. The Cherokee homeland is rich in caves. The karst geology of the Appalachian Valley and Ridge Province and the Cumberland Plateau produces cave systems throughout the region, and the Cherokee people lived alongside these features for thousands of years. Archaeologists have documented evidence of Cherokee presence in cave systems in their traditional territory. And scholars who have worked respectfully with Cherokee communities have noted that caves appear in recorded traditions as significant places, though the full meaning of those traditions belongs to the Cherokee people and their own interpretive frameworks. The Osage Nation, whose traditional territory encompassed large areas of what is now Missouri, Kansas, and Oklahoma, inhabited a landscape rich in caves and springs. The Ozark Plateau, the heart of Osage country, is one of the most cave-rich regions of the continent, and springs emerging from its limestone aquifers were significant features of the landscape. The Osage relationship with their homeland was one of deep and long-standing familiarity, developed over centuries of living within and moving through a particular landscape. What the specific character of the Osage relationship with the underground features of their territory was is a matter for Osage scholars and tradition keepers to address, and it is not appropriate for this documentary to speak on their behalf. The Hopi people of the Colorado Plateau have maintained, across many generations and through great historical disruption, a body of knowledge and tradition centered on their relationship with their homeland, a landscape of mesas and canyons, of ancient springs and the memory of water in a semi-arid world. Springs are of particular significance in Hopi tradition, as sources of life in a landscape where water is precious. The emergent stories that are central to Hopi cosmology, accounts of how the Hopi people came to be in this world, involve a movement from a world below to the world above, a transition through something like an opening in the earth. Hopi scholars and tradition keepers have been clear that these traditions carry deep significance and are not simply metaphors, but living expressions of a worldview that sees the underground world as continuous with and connected to the world above. It would be wrong to flatten this into a simple claim that the Hopi believe caves are entrances to other worlds and leave it at that. The tradition is richer and more complex than any such summary could convey. What can be said is that the boundary between the underground and the surface, between what is below and what is above, is a significant conceptual and spiritual boundary in Hopi tradition, one that is not a barrier but a permeable threshold. The Shawnee people, whose traditional territory ranged across much of the Ohio Valley and surrounding regions, inhabited a landscape that includes some of the most extensive cave country in North America. The cave systems of the Cumberland Plateau and the interior low plateaus were within the Shawnee world, and springs and underground water sources were features of a landscape that the Shawnee knew in great detail. The Shawnee were displaced repeatedly during the colonial period and forced to relocate, making the recovery of detailed traditional knowledge about specific landscape features difficult, but Shawnee communities today maintain connections to their ancestral traditions and their homeland. Among the Pueblo peoples of the American Southwest, a diverse group of nations including the Zuni, the various Keresan-speaking Pueblos, the Tiwa-speaking and Tewa-speaking Pueblos, and others, the relationship between water, springs, and the underground world is woven deeply into ceremonial and cosmological traditions. Many Pueblo traditions understand springs as places where the boundary between this world and an interior world becomes permeable, places where prayers and offerings can move in both directions, where the rain-bringing powers of the below can be communicated with. Springs are treated with care and respect, and ceremonies associated with water and rainfall are among the most important in many Pueblo ceremonial calendars. The Pueblo peoples also have long histories of relationship with the caves of their region. The caves of the Guadalupe Mountains, among them the cave system that would eventually be documented by American explorers and named Lechuguilla, are within the traditional territories of peoples who had been present in that region for thousands of years before European arrival. Archaeological evidence of human presence in the Guadalupe Cave country predates European contact by many centuries. What these very different nations, Cherokee, Osage, Hopi, Shawnee, Pueblo, share is not a single belief system or a common story about caves. What they share is something simpler and more fundamental, a long inhabitation of landscapes that include the underground world as a real and significant part of the environment, and the development over many generations of close attention to that landscape of relationships with it that are complex, meaningful, and deeply rooted. Every indigenous nation preserved its own unique history. This is a fact that cannot be stated often enough in discussions of this kind. The temptation to merge different nations' traditions into a single generic story, to speak of what Native Americans believed as if there were one unified body of belief, is a temptation that must be resisted. It does violence to the specificity and the dignity of each nation's own tradition. What we can observe, without overstepping, is that the indigenous peoples of North America brought to their experience of the underground world the same extraordinary depth of attention that they brought to every aspect of their landscapes. The caves and springs and sinkholes of the continent were not blank spaces on a map. They were known places, places with histories and meanings and relationships to the people who lived alongside them. That knowledge, accumulated over thousands of years of careful, patient attention to the land, is itself a remarkable form of exploration. There is something deeply moving about contemplating the fact that long before any European explorer set foot in North America, long before the first scientific survey of any cave system, long before the first map was drawn of a cave passage, the underground world of this continent was known. It was known in ways that no map could fully capture. It was known through generations of experience, through the stories that preserved that experience, through the ceremonies that maintained the relationship between communities and the places they depended on. The archaeology of deep cave exploration in the American Southeast tells us that people were venturing miles into cave systems with cane torches 4,000 years ago. The living traditions of indigenous nations tell us that the relationship between people and the underground world did not begin and end with a single expedition. It was sustained, renewed, deepened across generation after generation, for thousands of years. When European explorers and settlers arrived in North America and began to document the caves they found, they were, in virtually every case, discovering places that were already known. The caves that would later be named and mapped and celebrated as great natural wonders of America were already part of the human geography of the continent, already inhabited, in some sense, by the accumulated knowledge and relationship of the peoples who had lived alongside them for millennia. This is worth holding in mind as we turn now to the history of formal cave exploration in North America. The story of the men and women who began in the 18th and 19th centuries to venture into the caves with lanterns and mapping instruments to measure and record and document what they found. They were not discovering empty darkness. They were entering a world that had already been known in its own way for a very long time. And the story of what they found, and what they mapped, and what they realized they could not yet map, is a story of one of the great ongoing scientific adventures of the North American continent. It begins, like most great adventures, with one remarkable person willing to go further into the darkness than anyone before. There is a particular kind of courage that belongs to the underground world. It is not the loud, dramatic courage of battlefields or summits. It is quieter than that, more patient, more methodical, more attuned to the specific demands of a place that offers no mercy for carelessness and no shortcuts for the impatient. It is the courage of people who are willing to crawl through passages barely wide enough for a human body to lower themselves on ropes into vertical shafts, whose bottoms they cannot see, to wade through underground streams in the dark. And to do all of this not in a single burst of adrenaline, but steadily, carefully, hour after hour, with the knowledge that the way out is a long journey behind them, and that the only way to make it back safely is to pay very close attention to every detail of the world around them. The great cave explorers of North American history had this quality of patience. They had it in abundance. Their story begins, in the modern sense, in the 19th century, when a combination of growing scientific curiosity, expanding settlement into cave-rich regions, and the development of tourism around remarkable natural features began to draw systematic attention to the underground landscapes of the continent. But before the scientists arrived, before the tourists arrived, before the land surveys and the deed claims and the hotel brochures, there were the local people who already knew the caves. And among the most important of those people in the history of Mammoth Cave was a man named Stephen Bishop. Stephen Bishop was enslaved, the legal property, under the brutal system of American slavery, of the man who owned the land above Mammoth Cave in Kentucky. He was brought to the cave in the 1830s as a teenager to work as a guide for the visitors who were already beginning to arrive at what had become recognized as one of the great natural wonders of the continent. And what Stephen Bishop did in the years that followed transformed the understanding of Mammoth Cave more profoundly than any other single individual before the modern era. He explored it. With lanterns, the open-flame lard oil lanterns that were the standard lighting technology of the period, Stephen Bishop pushed into passages that no documented explorer had previously entered. He crossed the bottomless pit, a vertical shaft that had previously stopped exploration of a major section of the cave, by improvising a bridge from a cedar ladder. Beyond it, he found new passages, new chambers, new underground rivers, a whole section of the cave that had been unknown to the documented exploration of the time. He drew maps. The maps that Stephen Bishop produced of Mammoth Cave in the 1840s were remarkable documents, carefully observed, accurately proportioned, representing the cave system with a spatial understanding that reflected years of intimate familiarity with its passages and chambers. His map, published in various forms, was the most complete representation of Mammoth Cave available for many decades. He learned the cave in the way that people learn a landscape they live within, not as an abstraction, but as a living place with specific features, specific characters, specific moods. He knew where the ceilings were low and where they soared. He knew where the underground rivers ran and where they disappeared. He knew the passages that looped back on themselves and the passages that led somewhere new. Stephen Bishop spent years of his life in the cave, and he came to know it with extraordinary depth. He died in 1857, still enslaved, never having received either freedom or recognition commensurate with what he contributed to the exploration and documentation of one of the greatest natural wonders in North America. His grave is in the old Mammoth Cave cemetery on the property. He was, by any reasonable measure, one of the great cave explorers of the 19th century. The development of scientific speleology, the systematic study of caves as natural phenomena, proceeded along a separate track in Europe before it took firm root in North America. The French geologist Édouard Adalfred Martel is generally credited as the father of modern speleology. In the last decades of the 19th century and the early years of the 20th, Martel descended into cave systems across France, Spain, and other European countries, developing the equipment and techniques necessary for systematic underground exploration and documentation. He brought scientific method to cave exploration, measuring and recording, drawing careful maps, collecting geological and biological specimens, and publishing his findings for a scientific audience. Martel visited the United States in 1905 and explored Mammoth Cave, among other sites. His visit was significant not because he made dramatic new discoveries there, but because it represented a connection between the emerging European tradition of scientific speleology and the largely amateur, tourism-driven cave exploration culture of North America. In the decades that followed, American cave exploration began to develop a more systematic, scientific character. But before that scientific tradition fully flowered, there came a story that captured the attention of the entire country, a story that was not primarily about science or discovery, but about a man, a cave, and a tragedy that unfolded over days while the world watched. Floyd Collins was a Kentucky caver, the word most commonly used for people who explore caves recreationally, as opposed to speleologists who study them scientifically. He grew up near the cave country of Edmonson County, Kentucky, and spent much of his young life exploring the cave systems of the region with a passionate, almost obsessive interest. In January of 1925, while exploring Sand Cave, a cave on property that he hoped to develop as a tourist attraction, Collins became trapped when a rock shifted and pinned his ankle in a narrow passage deep inside the cave. He was alive. He was conscious. He could speak to rescuers who reached him through the passage, but he could not be freed. What followed over the next 18 days was one of the first great American media events. Reporters descended on the scene. Radio broadcasts carried updates across the country. Crowds gathered. Rescue attempts were made and complicated by the geology of the cave and by disagreements among the rescuers about the best approach. A shaft was dug from the surface in an attempt to reach Collins from above. Floyd Collins died before the shaft reached him. His body was eventually recovered, and his story became part of the folklore of American cave country. A cautionary tale about the dangers of solo caving, a human drama that humanized the underground world for millions of people who had never set foot in a cave. And an event that in some ways contributed to the growing public interest in cave exploration and cave science in the following decades. The National Park Service began conducting systematic cave surveys in the mid-20th century, as the parks that contained major cave systems grew in importance and as the need for accurate maps became more pressing both for visitor management and for scientific research. The survey of Mammoth Cave, conducted over many years by teams of volunteer cavers working in coordination with the National Park Service, gradually revealed the true extent of the system, an extent that repeatedly exceeded what surveyors had expected to find. Modern speleology in North America developed through the work of cave exploration clubs, grottos, in the terminology of the National Speleological Society, which was founded in 1941, whose members conducted both recreational caving and systematic exploration and mapping of cave systems across the continent. These groups, working on weekends and during vacations, in conditions of considerable physical difficulty and sometimes genuine danger, have collectively produced the detailed maps of North American cave systems on which all of the scientific work of the past several decades has been based. The work of these explorers, amateur and professional, historical and modern, has a particular quality of quiet dedication that is worth appreciating. Cave mapping is not glamorous work. It involves lying in mud, squeezing through narrow passages, sketching measurements by headlamp, and then returning to do it again and again and again as passage after passage is documented and added to the growing map. A cave system with hundreds of miles of passage was not mapped in a single expedition or a single year. It was mapped in small increments over decades by many different people working together. The courage involved is not the courage of a single dramatic moment. It is the quieter courage of sustained, patient, methodical engagement with a difficult and unforgiving environment, undertaken not for personal fame in most cases, but simply out of love for the underground world and a desire to understand it more fully. And what those decades of patient exploration have revealed is something that continues to astonish even people who have spent their careers studying caves. The underground world of North America is vastly larger than anyone imagined when systematic exploration began. Let us be still for a moment. Imagine standing at the entrance of a cave at night. The surface world is quiet, the kind of quiet that belongs to rural places far from cities and highways, where the only sounds are the wind in the trees and the occasional call of a night bird. The cave entrance is a dark oval in the hillside before you. A breath of cool air moves outward from it, the cave exhaling gently in the darkness. You can feel the temperature drop slightly as you approach. Now imagine that behind that entrance, stretching away into the rock beneath the hill and the ridge and the plateau beyond, there are more than 400 miles of mapped passage. not 400 feet, not 400 yards, 400 miles. And beyond the mapped passages, beyond the furthest point any surveyor has yet reached, there are more passages whose existence can be inferred from the way the air moves and the way the water drains, but whose extent is still unknown. This is Mammoth Cave. Mammoth Cave National Park in south-central Kentucky contains the longest known cave system in the world, with more than 400 miles of surveyed passages as of the most recent published surveys. The number has grown steadily over the decades of systematic exploration, and there is no reason to believe that the mapped portion represents the full extent of the system. Exploration continues. New passages are found. The map grows. To hold the scale of this in the mind requires a deliberate effort. 400 miles is roughly the distance from New York City to Boston and back again. It is the distance from Chicago to St. Louis and partway back. If you were to walk every mapped passage of Mammoth Cave at a comfortable pace, allowing for the time needed to navigate crawlways and climb formations and wade through underground streams, it would take you many weeks to complete the journey. The cave developed in the limestone and sandstone formations of the Mammoth Cave Plateau, a broad upland underlain by thick sequences of Mississippian limestone. Its formation has been occurring for at least 1 million years, driven by the slow downward cutting of the Green River Valley, which provides the base level for the cave's drainage. As the Green River cut deeper into the surrounding terrain, the water table in the cave dropped, leaving upper passages dry and allowing new passages to form at lower elevations. The result is a multi-level cave system of extraordinary complexity, passages at several different elevations, connected by vertical shafts and sloping corridors, with an active stream level at the base, carrying the cave's underground rivers toward their emergence points along the Green River. Mammoth Cave was connected underground in 1972 to the Flint Ridge Cave system, a connection that, when it was confirmed after years of effort by a team of cave explorers, instantly doubled the known length of the combined system and demonstrated that what had been thought of as separate caves were in fact parts of a single enormous labyrinth. That connection was found by a small team of explorers who spent hours in difficult, wet, flood-prone conditions following a lead that others had considered too marginal to pursue. It is one of the great moments in the history of American cave exploration. But Mammoth Cave is not the only extraordinary system beneath North America. In the Guadalupe Mountains of southeastern New Mexico, there lies a cave that is, in many ways, the most scientifically remarkable cave system in North America. It is called Lechuguilla Cave, and it was not known to exist in its full extent until 1986, when a group of explorers, working on a lead that had been discussed among cavers for years, a rubble-filled pit in Carlsbad Caverns National Park that produced a detectable air flow, finally dug through the breakdown blocking its entrance and descended into a cave system that stunned even experienced speleologists. Lechuguilla Cave extends to a depth of more than 1,600 feet below the surface, making it the deepest cave in the continental United States, and has more than 150 miles of surveyed passage. but its significance is not primarily in its length or depth. It is in its extraordinary geological character. The cave formed through a process called sulfuric acid speleogenesis, a process fundamentally different from the rainwater dissolution that created most of the caves discussed so far. Hydrogen sulfide gas, rising from hydrocarbon deposits deep in the earth, mixed with oxygen-bearing groundwater to produce sulfuric acid. This acid ate into the limestone from below, hollowing out passages and chambers in a pattern quite different from the stream-carved passages of a cave like Mammoth. The result is a cave of breathtaking, alien beauty, enormous chambers draped with formations found almost nowhere else on Earth. The gypsum formations of Lechuguilla are extraordinary. Gypsum chandeliers, fragile, branching structures of crystalline calcium sulfate, hang from the ceilings of some chambers, some of them many feet in length. Pools of extraordinarily pure water reflect the cave ceiling with mirror-like clarity. The walls are encrusted with bizarre mineral formations, snowy gypsum flowers, curving helictites, massive selenite crystals that represent conditions of formation unique to this cave's unusual chemistry. Lechuguilla is strictly protected. Access is limited to research teams and permitted scientific expeditions. The cave's extraordinary fragility, the formations can be destroyed by a single misplaced handhold, and the microbial communities in its pools are uniquely sensitive to contamination, demands an extreme level of care. This is not a cave you can visit as a tourist. It is a cave that exists, in its full extent, only for the benefit of science and for the long future of the Earth. Beneath the Black Hills of South Dakota lie two cave systems that have their own extraordinary characters. Jewel Cave in Custer County, South Dakota, is currently the third longest known cave in the world, with more than 200 miles of surveyed passage. It takes its name from the calcite crystals, nailhead spar, that line its passages with a sparkling, jewel-like coating. The cave formed in Mississippian limestone and has a complex history of formation phases, including both water table and vadose development. Exploration of Jewel Cave has been ongoing since its discovery by prospectors in 1900, and new passage continues to be found. The cave breathes, it inhales and exhales strongly through its entrance, depending on atmospheric pressure changes, suggesting that the mapped portion of the system is connected to a much larger volume of underground space that has not yet been explored. Wind Cave. A few miles to the south of Jewel Cave has more than 150 miles of surveyed passage and is famous for a formation type called boxwork, thin blades of calcite that project from the cave walls in honeycomb-like patterns. Formed by an unusual geological process and found in few caves anywhere in the world with the density and extent that characterizes Wind Cave. Wind Cave is also notable as one of the sites sacred to the Lakota people, whose traditions speak of it as a place of emergence. The cave breathes through its natural entrance with considerable force, and the barometric wind that flows in and out gave it the name by which it is known to American visitors. The Ozark Plateau of Missouri and Arkansas hosts cave systems that have been explored and studied for more than a century, yet continue to yield new discoveries. The caves of this region formed in ancient dolomite and limestone formations, and they are notable for their underground rivers and springs. Mammoth Cave in Missouri, now known primarily as part of Silver Dollar City, was explored by members of the British Speleological Association in the 1950s, and the cave country of the Ozarks attracted systematic exploration from the mid-20th century onward. Ozark Underground Laboratory in Missouri has been used for biological research on cave ecosystems. The Ozark Caves are deeply connected to the region's hydrology. The springs that emerge from their aquifers are among the largest in the country, and the cave systems feeding them extend for distances that are still not fully documented. The Appalachian Cave region, the cave systems of Virginia, West Virginia, and the surrounding states, contains cave systems of considerable length and complexity. Breathing Cave in Bath County, Virginia, is one of many examples of a cave system whose airflow suggests connections to unmapped sections. Organ Cave in West Virginia has been explored for more than 2 centuries. It was known to European settlers in the colonial era and was mined for calcium nitrate during the American Civil War, and its passages extend for many miles. The caves of the Greenbrier Valley of West Virginia form a cluster of known cave systems that hydrological evidence suggests may be connected underground in ways that have not yet been documented through direct exploration. And then there are the lava tubes. In the volcanic regions of the American West, the Columbia Plateau of Washington and Oregon, the Snake River Plain of Idaho, the volcanic fields of the Modoc Plateau in northeastern California, and the Coconino Plateau in Arizona. And the Big Island of Hawaii, lava tube caves exist in great numbers. These caves formed not by dissolution of limestone, but by the physical process of lava flowing beneath a solidified crust. As the lava flow advanced and then drained away at the end of a volcanic eruption, hollow tubes of solidified basalt were left behind. Lava tube caves can be very long. Kazumura Cave on the Big Island of Hawaii is the longest and deepest known lava tube in the world, extending for more than 40 miles. On the mainland, the lava tube systems of the Modoc Plateau and the Snake River Plain include many caves of considerable length that have not been fully explored. The Lava Beds National Monument in Northern California contains more than 800 cave entrances representing numerous lava tube systems, many of which have not been fully surveyed. The question that hangs over all of this, the question that has motivated cave explorers for as long as they have been exploring, is the one this documentary has been building toward since its first moments. How many miles of underground passages remain hidden simply because no human has yet reached them? The honest answer is that nobody knows, and the uncertainty is not a small one. It is not the uncertainty of being off by a few percent. It is the uncertainty of a field in which major discoveries that double or triple the known length of a cave system, continue to be made. The connection of Mammoth Cave to the Flint Ridge system in 1972 was not predicted with confidence beforehand. The full extent of Lechuguilla Cave was completely unknown until 1986. The survey of Lechuguilla Cave has been ongoing for more than a century, and new passages continue to be found. In cave after cave, system after system, the story repeats. Explorers push a little further, squeeze through a little more, follow the airflow a little more patiently, and find more cave. There are entire regions of North America with karst geology, regions with the right rock type, the right hydrology, the right geological history to contain extensive cave systems that have not been explored at depth. There are areas where the cave entrances are flooded for most of the year, limiting access. There are areas where the cave passages are simply too small for a human being to enter, but where water flows freely, and where the passages clearly enlarge somewhere beyond the point of human entry. There are areas where the terrain is so remote, so difficult to access, that systematic exploration has barely begun. The great cave systems of North America are not well understood relics of a completed natural history. They are living, active, still being discovered features of a continent that continues to yield new knowledge to patient and careful explorers. The labyrinth is in a very real sense infinite, not literally infinite of course, but infinite in the sense that matters most practically, infinite relative to the human capacity to explore it, infinite in the time it would take to fully map it, infinite in the number of questions it raises for everyone it answers. There is a particular kind of wonder that belongs to this realization. It is a quiet wonder, not the sharp excitement of a sudden revelation, but the slow, spreading sense of being in the presence of something vast and patient, and fundamentally beyond the scale of any single human life. The caves beneath North America have been forming for millions of years. They will continue forming for millions of years more. The portion of that time during which human beings have been exploring them is infinitesimally small. And yet the exploration continues, candle by candle, headlamp by headlamp, survey station by survey station. And each small increment of knowledge adds to the growing picture of a world that, the more it is explored, the more extraordinary it reveals itself to be. There is something about the underground world that has always stirred the human imagination. Perhaps it is the darkness, the complete, total, absolute darkness that exists in a cave beyond the reach of any surface light. People who have experienced true cave darkness, who have turned off their lights in a passage far from the entrance and sat quietly in it, often describe the experience as unlike anything they have encountered above ground. It is not simply the absence of light. It is the presence of something, a quality of darkness that feels almost material, almost textured, as if the dark itself has substance. Perhaps it is the silence. Cave silence, like cave darkness, has its own particular quality. It is not the silence of an empty room or a quiet forest. It is a silence in which you can hear your own heartbeat, your own breathing, the slight movement of air past your skin. It is a silence that has never been broken by traffic noise or aircraft or the distant hum of human industry. It is, in a meaningful sense, primordial silence, silence that has been unbroken since the passage was first formed. Perhaps it is the scale, the disorienting experience of standing in a chamber whose ceiling is 50 feet above you, and whose walls are 100 feet to either side, knowing that you are inside a mountain, that millions of tons of rocks surround you in every direction, that the world you came from is somewhere above. Whatever the reason, caves have been the subject of folklore and storytelling in virtually every culture that has lived near them. North America is no exception. It is important to be clear about what we are doing in this chapter. The stories we are about to describe belong to regional folklore, to the oral traditions of particular communities, to the storytelling cultures of specific times and places. They are not historical evidence of hidden kingdoms or underground civilizations. They are not scientific claims. They are expressions of the human imagination in response to the experience of the underground world, and as such, they are interesting and worth preserving, but they should be understood for exactly what they are. With that said, the folklore of caves in North America is rich and varied and atmospheric enough to be worth exploring for the texture it adds to the story of the underground world. Among the most widespread categories of cave folklore across North American regional traditions is the idea of the hidden entrance, the notion that somewhere in a particular landscape, behind a waterfall or beneath a ledge of stone or at the bottom of a particular sinkhole, there is an entrance to a cave system of extraordinary extent. This entrance, in the folklore, is difficult to find and may only be accessible at certain times. What lies beyond it is described variously as a vast underground network of passages, a series of chambers of great beauty, or simply an endless dark corridor leading into the earth. This category of folklore is easy to understand in a landscape where caves genuinely do have hidden entrances, where the only sign of a cave beneath the ground is a small airflow from a gap in a hillside or a depression in a forest floor, or a spring of unusually cold water emerging from a limestone bluff. In karst country, the ground is genuinely full of passages that are not obvious from the surface. The folklore simply takes a real feature of the landscape and extends it imaginatively. The idea of lost explorers is another recurring theme in cave folklore across North America. Stories of people who entered caves and did not come out, who followed passages that no one had previously entered and were never seen again. Some of these stories are entirely fictional. Some may reflect real historical incidents. The cave country of Appalachia and the Ozarks had its genuine accidents, its genuine tragedies, its genuine stories of people who went underground and encountered difficulties. The Floyd Collins story, which we discussed in the previous chapter, is a historical event that has the shape and character of folklore, and it has indeed been retold and embellished in the folk traditions of the region. Stories of hidden treasure have attached themselves to caves throughout North American history. The cave country of Missouri and Kentucky and Tennessee has generated numerous folk accounts of caves used as hiding places for gold or silver, by outlaws, by Civil War soldiers, by earlier inhabitants whose identity shifts with the telling. None of these treasure stories has ever been verified by archaeological evidence, but they persist generation after generation because the cave is the perfect imaginative container for a hidden thing. Cave spirits and supernatural cave inhabitants appear in the folklore of many regional traditions across North America. These figures vary enormously. Some are dangerous, some protective, some simply mysterious. They inhabit the darkness in the way that any unknown space generates imaginative inhabitants. The cave, in regional folklore, is almost always a liminal space, a threshold between the known world and something that lies beyond it, something that requires a particular kind of courage or knowledge to approach. Some of the most elaborate cave folklore involves the idea of underground kingdoms, self-contained worlds existing somewhere beneath the surface, with their own landscapes and populations and histories. These stories appear in various forms across different regional traditions and different time periods, and they share the quality of imagining the underground not as an empty space, but as a parallel world with its own complex geography. Again, to be absolutely clear, there is no archaeological or geological evidence for any underground human civilization in North America. The caves of this continent have been explored by scientists who have found stone and water and air, remarkable geology and extraordinary biology, and the traces of ancient indigenous activity that we discussed in earlier chapters. They have not found kingdoms or civilizations. The underground kingdom stories belong to the realm of imagination, not the realm of historical fact. But imagination is not nothing. The folklore of caves tells us something true about the human response to the underground world, something about the way the darkness and the scale and the strangeness of cave environments stimulates the storytelling, impulse the need to populate unknown spaces with narrative. To make sense of places that resist easy sense-making. These stories are part of the human relationship with the underground world, and they deserve to be recognized as such, as long as they are not mistaken for something they are not. There is a certain pleasure in the cave folklore of North America, a quality of mystery and imagination that enriches the experience of thinking about the underground world, as long as we hold it lightly, as long as we know it for what it is. The caves themselves are extraordinary enough without embellishment. They are full of things stranger and more beautiful than any folklore has imagined, and some of those things are alive. Turn off the light, not the lamp in the corner of the room, not the glow of a screen, but imagine, for a moment, turning off every source of light in a space and sitting in true, complete darkness. No photons entering the eye at all. No gradual adjustment that allows shapes to emerge from the shadows. Nothing. Now imagine living there, not visiting, not sheltering temporarily, but living, eating, moving, reproducing, evolving in that darkness, generation after generation, for thousands of years, for tens of thousands of years, for millions of years. This is what life has done in the caves of North America, and what it has produced through the slow, patient pressure of evolutionary time in conditions of radical isolation and permanent darkness, is among the most extraordinary biological phenomena on the continent, a collection of creatures so specialized, so perfectly adapted to their strange and lightless world that they seem at first glance to belong to another planet entirely. Cave biology, the study of life in cave environments, is a field that has developed enormously over the past century. And what it has revealed about the underground ecosystems of North America challenges many of our intuitions about what life requires, and about how radically living things can change when the pressures of their environment shift over geological time. Let us begin with what is perhaps the most immediately striking feature of cave life: the loss of eyes. In cave after cave across North America, species that descended from surface ancestors with fully functional vision have, over the course of thousands of generations in complete darkness, lost the use of their eyes entirely. This is not a dramatic event. It happens gradually over many generations as the cost of building and maintaining a complex visual organ outweighs its benefit in an environment where there is nothing to see. Eyes are metabolically expensive. They require significant biological resources to construct and maintain. In a light-filled environment, that expense is justified by the survival benefit that vision provides. In complete darkness, where vision cannot function regardless of the quality of the visual organ, the cost remains, but the benefit disappears. Individuals with slightly reduced eyes, slightly less metabolic demand, may have a subtle survival advantage. Over thousands of generations, that slight advantage compounds, and the visual apparatus is gradually reduced, generation by generation, until what remains is either a vestigial remnant buried beneath the skin or nothing at all. The result is animals that are blind not by injury or disease, but by evolutionary design, creatures for whom darkness is not an absence, but simply the normal condition of existence. The most famous example in North American cave biology is probably the blind cavefish. The southern cavefish, Typhlichthys subterraneus, is found in cave systems across the interior highlands of the American South and Midwest, in the cave streams of Kentucky, Tennessee, Missouri, Arkansas, and surrounding states. It is a small fish, pale and slender, with no functional eyes. Its skin has little or no pigmentation. There is no evolutionary pressure to produce the melanin that provides protective coloration in surface fish, because there is no light to cause the cellular damage that pigmentation guards against, and because there are no visual predators to hide from. What the southern cavefish has instead of eyes and pigmentation is an extraordinarily developed lateral line system, a network of sensory organs along its body that detects minute vibrations and pressure changes in the water around it. This system, which all fish possess to some degree, has been elaborated in the southern cavefish to a remarkable degree of sensitivity. The fish navigates, finds prey, and interacts with its environment through touch and vibration and the detection of water movement. A sensory world utterly foreign to our own visual experience, but perfectly suited to the streams of cave darkness. In the cave streams of the Ozarks, the Ozark cavefish, Amblyopsis rossi, occupies a similar ecological niche. In the cave systems of the Appalachian region, the Tennessee cavefish and other related species have undergone similar evolutionary journeys. Each cave system, or cluster of connected cave systems, has its own population of cave-adapted fish, isolated from populations in other systems, evolving independently, accumulating its own particular suite of adaptations. This pattern of isolation and independent evolution is one of the defining features of cave biology. Because cave populations are cut off from surface populations, and often from other cave populations, by the rock that surrounds them, they evolve in isolation. The result is an extraordinary diversity of highly localized species, many of them found in a single cave system or even a single section of a single cave system, and found nowhere else on Earth. The implications of this for conservation are sobering. A species found only in one cave system is a species that can be rendered extinct by a single event: a contamination of the water supply, a collapse of the cave environment, a change in the hydrology that drains the stream or floods the air passages. The biological communities of North American caves are among the most vulnerable ecosystems on the continent precisely because of their extreme localization. Beyond fish, the cave ecosystems of North America include a remarkable array of other inhabitants. Cave salamanders represent another group in which cave adaptation has proceeded to striking extremes. The grotto salamander, Eurycia spelea, found in caves of the Ozark Plateau, begins its life as a normally pigmented larva with functional eyes in the surface streams that feed the cave systems. But as it matures and moves deeper into the cave environment, it undergoes a transformation. Its eyes cloud over and become non-functional, its pigmentation fades, and it becomes the pale, eyeless adult cave salamander. This transformation, metamorphosis, producing a cave-adapted adult from a surface-adapted larva, is a remarkable example of developmental plasticity in the service of cave life. The Texas blind salamander, Eurycia rathbuni, found in the underground waters of the Edwards Aquifer beneath San Marcos, Texas, represents one of the most extreme cave adaptations among North American amphibians. It is a slender, ghostly white creature with external gills it retains throughout its life. It never fully metamorphoses in the way surface salamanders do, with tiny vestigial eyes visible as dark spots beneath the skin. It feeds on cave shrimp and small invertebrates in the lightless waters of one of the most important aquifers in Texas, and it exists only in those waters. Its entire global range is the underground portion of the Edwards Aquifer in a relatively small area of central Texas. Cave shrimp are another characteristic element of cave aquatic communities. The Alabama cave shrimp, Palimonias alabami, is found in a handful of cave systems in the Tennessee River drainage of northern Alabama, and like so many cave species, it is found nowhere else. It is small and pale and carries on its existence in underground streams that have never felt sunlight, feeding on organic matter washed in from the surface world above, on microbial films that grow on cave surfaces, on whatever the slow trickle of energy from the world above provides. Because caves are almost entirely cut off from photosynthesis, the process by which surface ecosystems ultimately derive their energy from the sun, cave ecosystems must find their energy elsewhere. The organic matter that enters caves through sinking streams, through animal droppings, particularly from cave-dwelling animals like bats and cave crickets that forage outside the cave and return, and through the slow seepage of dissolved organic compounds through the rock, forms the base of most cave food webs. Cave crickets are a particularly important element of this energy transfer. Many species of cave crickets roost in caves during the day, but venture out onto the surface at night to forage. They return to the cave carrying nutrients from the surface world in their bodies, and their droppings accumulate on the cave floor and provide a significant energy subsidy to the cave ecosystem. Invertebrates that feed on the cricket droppings, cave beetles, cave millipedes, various other cave-adapted arthropods, are themselves fed upon by cave salamanders and cave fish, completing a food chain that is ultimately dependent on the surface world, but expressed entirely in darkness. In some cave systems, however, a truly remarkable form of energy production occurs that owes nothing to the surface world at all. In Lechuguilla Cave and in several other cave systems formed through sulfuric acid speleogenesis, microbial communities have been discovered that derive their energy not from photosynthesis, not from sunlight directly or indirectly, but from chemosynthesis. These bacteria oxidize hydrogen sulfide or other reduced chemical compounds, using the energy released by this chemical reaction to produce organic matter. They are, in a meaningful sense, independent of the sun. They represent a self-contained biological system, deriving energy from the chemistry of the rock and water around them, and supporting small but genuine food webs. The discovery of these chemosynthetic microbial communities in caves has had implications beyond cave biology. It has informed the scientific discussion of whether life might be possible in environments entirely lacking sunlight. On other worlds, for example, where the chemical conditions might support similar chemosynthetic processes. The caves of the Guadalupe Mountains have become, in a sense, a research site for understanding the potential of life in environments utterly unlike the sunlit surface of our world. The white films and amber-colored sediments produced by these cave microbial communities, sometimes called snotites, for the unlovely but accurate description of their appearance, are not simply interesting biological curiosities. They are actively participating in the chemistry of the cave environment, contributing to the dissolution of the rock and to the deposition of certain mineral formations. They are part of the geological story as well as the biological one. Evolution in the cave environment has also affected behavior, physiology, and metabolism. Many cave animals have reduced metabolic rates compared to their surface relatives, a useful adaptation in environments where food is scarce and unpredictable. They can survive for long periods without food. They grow slowly. They live a long time. They reproduce slowly. This life history strategy, slow growth, low energy demands, long lifespan, is characteristic of animals living in resource-limited stable environments, and the cave is perhaps the most stable environment on Earth. Temperature does not vary with the seasons. Humidity is nearly constant. The darkness is never broken. In such a place, patience is the supreme survival strategy. There is something deeply moving about the life in these caves, something that connects, in an unexpected way, to the geological story of the caves themselves. The limestone was laid down by the patient accumulation of billions of small marine organisms over millions of years. The caves were carved by water moving through rock over hundreds of thousands of years. The life within the caves evolved through the slow, patient pressure of natural selection over thousands of generations. Everything in the cave world operates on timescales that dwarf the human experience of time. And the creatures that live in the cave darkness are exquisitely, precisely what they are, not because of any plan or intention, but because of the patient pressure of time on living things, the same patient pressure that shaped the stone and carved the passages and deposited the formations. They are the living expression of geological time, as surely as the stalactites and the flowstone and the ancient dissolved limestone that surrounds them. There is a moment in the exploration of a new cave passage, a moment that every cave explorer who has pushed into unknown territory will recognize, when the passage you have been following opens suddenly into a larger space. Your headlamp, which has been illuminating a confined corridor of stone only a few feet wide and perhaps 5 feet tall, suddenly finds nothing to illuminate. The beam travels outward into darkness and does not return from any nearby surface. The sound of your movement changes, the close, tight sound of a confined passage replaced by the diffuse, echoing quality of a larger space. You step forward, the floor drops slightly, and slowly, as you move your light around, the shape of a new chamber emerges from the darkness. You are the first human being to stand in this space. Everything you see, the ceiling above you, the walls to either side, the floor beneath your feet, the formations on the walls, if there are formations, has never been observed before. It has existed in complete darkness for thousands or hundreds of thousands of years, waiting without waiting as stone waits for this moment. It is a feeling that no technology can fully replace, but technology has transformed what happens next for most of the history of cave exploration. Mapping a cave passage meant measuring it with physical instruments, a tape measure for distances, a compass for directions, a clinometer for vertical angles, and recording those measurements in a notebook before sketching the shape of the passage around the survey line. This method, called compass and tape surveying, is still used in cave exploration today because it is reliable, requires minimal equipment, and can be performed by small teams in difficult conditions. The maps it produces, when done carefully, are accurate and useful, but compass and tape surveying is slow. It requires that every section of a passage be physically entered and measured. It produces a representation of the cave that is, in essence, a centerline with a passage shape sketched around it, a two-dimensional simplification of a three-dimensional reality. Modern technology has added tools of extraordinary power to the Cave Mapper's toolkit. LiDAR, light detection and ranging, is perhaps the most transformative. A LiDAR scanner emits pulses of laser light and measures the time it takes for each pulse to return after reflecting from a surface. By emitting millions of pulses in all directions and recording the return time of each one, the scanner builds up a point cloud, a three-dimensional representation of the space around it, with millions of individual data points defining the surfaces of the cave walls, ceiling, and floor. A LiDAR scan of a cave passage takes minutes to acquire and produces a model of the space that is accurate to within a centimeter or less. Multiple scans, taken from different positions in the cave, can be registered together to produce a complete three-dimensional model of a cave section. When these models are combined across an entire cave system, the result is a three-dimensional map of the cave of extraordinary detail and accuracy. A map that shows not just the centerline and general passage shape, but every stalactite, every boulder, every change in floor level. Every ledge and crack and arch. These three-dimensional cave models have scientific uses far beyond simply knowing the shape of the passage. They can be used to calculate the volume of individual cave chambers and of the cave system as a whole. They can be used to analyze the geometry of cave passages in ways that reveal the history of their formation. They can be combined with geological data to understand the relationship between the cave's structure and the structure of the surrounding rock. And they create a permanent, precise record of the cave's condition at a particular moment in time, a baseline against which future changes can be measured. Ground-penetrating radar, GPR, extends the cave mapper's reach beyond the walls of the cave itself. By emitting radio waves into the rock and measuring the reflections from subsurface features, GPR can detect voids, potential cave passages, in the rock around and beneath known cave sections. This allows explorers to identify promising targets for further investigation without having to physically enter every potential lead. If GPR indicates a large void beyond a wall that appears solid, explorers know to look more carefully for a passage that might connect to it. Cave diving has opened an entirely different category of exploration. In many cave systems, some of the most significant passages are completely flooded sumps, in the terminology of cave explorers, that can only be entered by swimmers equipped with scuba or rebreather diving equipment. Cave diving is among the most technically demanding and genuinely dangerous forms of exploration practiced by human beings. The margin for error in cave diving is extremely small. A diver who runs low on air, or whose equipment fails, or who loses orientation in flooded passages may have no escape route. The skills required, navigation, gas management, buoyancy control in confined spaces, emergency procedures, take years to develop. But the passages that cave divers have explored in flooded sections of North American cave systems have revealed some of the most significant discoveries in modern speleology. In the cave systems of the Florida Peninsula, a region of extraordinary karst development in limestone and dolomite, cave divers have documented hundreds of miles of completely submerged passage in systems like Wakulla Springs and the Woodville Karst Plain. These are not simply flooded passages of modest extent. They are enormous, labyrinthine systems of submerged cave that extend for many miles and descend to considerable depths, carrying the underground drainage of a significant portion of northern Florida toward the coast. The exploration of these submerged systems has required the development of specialized equipment and techniques, including the use of rebreather technology, which recycles the diver's exhaled gas rather than releasing it as bubbles, significantly extending the range that can be reached on a single dive, as well as the development of rigorous safety protocols that have over time reduced but not eliminated the serious risks of the activity. Hydrogeological research, the scientific study of underground water systems, continues to reveal new connections between cave systems that were previously thought to be unrelated. Isotopic analysis of cave water can trace its origin and travel history. Chemical analysis of the water emerging from springs can reveal information about the cave systems through which it traveled. Modern dye tracing techniques, using more sensitive detectors than earlier methods, can detect connections over much greater distances. Climate research in caves has emerged as one of the most important applications of cave science in recent decades. Cave formations, particularly stalagmites and stalactites, record detailed information about the climate conditions that prevailed during their growth. The oxygen isotope ratios preserved in the calcite of a stalagmite reflect the temperature and source of the rainfall that produced the water that built the formation. Trace element concentrations reflect the chemistry of the soil through which the water passed. Growth rate reflects the amount of water flowing through, a proxy for rainfall. By analyzing these proxies layer by layer, drilling into a stalagmite, and sampling the calcite at intervals corresponding to decades or centuries of growth, scientists can reconstruct detailed records of past climate change that extend back hundreds of thousands of years. These cave climate archives, paleoclimate records preserved in the darkness, are some of the most valuable natural archives on the planet. They exist in caves precisely because the cave environment is so stable. A stalagmite in a cave has been growing, undisturbed, accumulating its chemical record for hundreds of thousands of years, while the surface world above it has experienced ice ages and warm periods, droughts and floods, the rise and fall of forests and grasslands. The record is there if scientists have the tools to read it. DNA sampling in caves has opened another frontier. Environmental DNA, genetic material shed by organisms into the water or sediment of the cave, can be collected from cave streams and analyzed to identify the species present, including species too rare or too cryptic to be directly observed. This technique has revealed the presence of species in cave systems that were not previously known to inhabit them, and it has provided new information about the connectivity between different cave populations. Ancient DNA extracted from cave sediments has revealed the presence of species, and in some cases, human populations at specific cave sites thousands of years ago. Modern cave expeditions are complex logistical undertakings. A research expedition to a major cave system might involve teams of cavers working in coordination over several days, establishing camps deep within the cave, ferrying equipment through difficult passages, conducting systematic surveys of new sections, while other team members document geology or collect biological or water samples. Communication between teams within a cave is challenging. Cave radio systems exist but have limitations, and the coordination of multiple simultaneous activities in a complex underground environment requires careful planning and clear protocols. The scientific yield from such expeditions, however, is remarkable. A single well-organized expedition to an unexplored section of a major cave system can produce survey data, geological samples, biological specimens, water chemistry measurements, and photographic documentation that will take months or years to fully analyze. Each expedition adds to the growing picture of a world that reveals more complexity the more carefully it is studied. And every year, somewhere in North America, a cave exploration team pushes past the end of the existing survey and finds more cave. Sometimes a little more. Sometimes a great deal more. Sometimes the discovery is geologically unremarkable, a continuation of a known passage type, extending in a predictable direction. But sometimes, not often, but sometimes, what lies beyond the end of the known passage is something that stops the explorers in their tracks. A chamber of extraordinary size, a formation of a type not previously seen in that cave. A crystal pool of such clarity that the formations reflected in it are indistinguishable from the formations themselves. Or simply more passage, extending away into the darkness, beyond the reach of the headlamps, going somewhere that nobody has yet been. The cave continues. It always continues. There is a map of North America that does not yet exist. It is a map of the underground, a complete representation of all the cave passages, all the flooded conduits, all the aquifer systems, all the lava tubes, all the rock shelters and pit caves and sea caves and talus caves that lie beneath the surface of the continent. A map that shows not just the known passages, the 400 miles of Mammoth Cave, the 150 miles of Lechuguilla, the 200 miles of Geological Cave, but every passage that exists, whether or not a human being has yet entered it. That map, if it could somehow be made, would be extraordinary. Geologists estimate that the karst regions of North America, the areas where the geology is suitable for cave development, and where cave systems have been confirmed to exist or are expected to exist, cover an enormous portion of the continent. The precise figure is difficult to calculate because karst geology exists at varying depths and with varying degrees of development across different regions, and because the definition of what constitutes a significant cave system involves judgments that reasonable scientists can differ on. But consider this. The mapped cave systems of North America represent the passages that explorers have physically entered and surveyed. They represent what is accessible, what has entrances large enough for a person to enter, what has not been permanently flooded, what has not been sealed off by rockfall, what explorers have actually reached. They do not represent the full extent of the underground drainage systems they belong to. Every major cave system in North America shows evidence of extension beyond its currently surveyed limits. Mammoth Cave breathes. Its air circulation indicates connections to large unmapped volumes of underground space. Geological Cave breathes with enough force to have alerted its discoverers to its existence before they entered it, and the volume of air it exchanges with the atmosphere indicates that the known cave represents a relatively small portion of a much larger underground system. Wind Cave breathes so strongly through its natural entrance that early visitors were knocked back by the airflow. Lechuguilla shows hydrological connections to portions of the surrounding karst that have not been directly explored. The unmapped cave passages of North America are not unmapped because of deliberate secrecy or because their existence is somehow suppressed. They are unmapped because the work of mapping them is genuinely difficult, genuinely time-consuming, and genuinely limited by physical and logistical constraints. Some passages are too small for a human body. Some are permanently flooded. Some are accessible only to highly trained cave divers willing to push far into flooded systems. Some are in remote areas where the logistical difficulty of mounting expeditions is very high. Some have not yet been found at all, their entrances hidden, their existence only inferred from the hydrology of the region above them. The question of how much cave remains undiscovered is one that serious researchers approach with a combination of scientific methodology and honest uncertainty. Hydrological modeling, building mathematical models of underground water flow based on the geology of a region, the location of recharge areas, and the location of springs, can identify where cave systems are likely to exist and estimate how large they might be. Dye tracing can confirm connections between different parts of a karst system and give information about the nature of the conduits connecting them. Geophysical surveys, including GPR and certain forms of seismic analysis, can identify voids in the rock. But none of these methods can substitute for the experience of physical exploration. The cave has to be entered, the passage has to be followed, the measurements have to be made. And the simple truth is that there are not enough people equipped with enough time and resources to explore all of the cave systems of North America within any human lifetime. The task is larger than the community of explorers. It will take generations to complete, if it can be completed at all, which is genuinely uncertain. The climate archives preserved in cave formations represent perhaps the greatest scientific resource that remains to be fully exploited in North American caves. Paleoclimate records from cave formations in the well-studied cave systems of the continent have already contributed significantly to our understanding of climate history over the past few 100,000 years. But there are cave systems in regions of North America whose paleoclimate records have barely been studied. The caves of the Ozarks, the caves of Appalachia, the caves of the desert Southwest, each of which potentially holds detailed records of regional climate history that would complement and extend the existing global record. These records matter not simply as historical curiosities, but as scientific data relevant to understanding how climate systems operate and how they have responded to past changes in atmospheric composition and solar forcing. As the global scientific community works to understand the causes and likely future trajectory of current climate change, the paleoclimate data preserved in cave formations is among the most valuable evidence available. The aquifer systems that feed North American springs and caves represent another domain of enormous scientific and practical uncertainty. The Edwards Aquifer beneath central Texas, the Floridan Aquifer beneath the southeastern coastal plain, the karst aquifers of the Ozarks and the interior low plateaus. All of these systems provide drinking water for millions of people, and all of them are imperfectly understood in terms of their full extent, their capacity, their recharge rates, and their vulnerability to contamination and over-extraction. Understanding these aquifers better, mapping the cave systems that form their conduits, studying the flow paths that connect recharge areas to discharge springs, is not simply an academic exercise. It is a matter of genuine practical importance for the communities that depend on them. And the work of understanding them is cave work, the patient, difficult, technically demanding work of going underground and finding out what is there. The question of ancient migration routes through cave systems is another area where significant uncertainty persists. Archaeological evidence has documented human presence in caves across the continent going back thousands of years. But the full record of that presence, the full story of how people moved through the cave-rich regions of the continent, what they were doing in the caves, what routes they followed, what knowledge they accumulated, is far from complete. New archaeological discoveries in cave sites continue to be made, and each one adds to a picture that is still incomplete in many of its details. What remains unknown in the underground world of North America is not a small residual quantity, a few loose ends to be tied up by the next generation of researchers. It is a vast, genuine, fundamental uncertainty. The known cave systems are impressive, but they are islands of documented knowledge in a sea of uninvestigated possibility. This is not a statement of failure. It is a statement of scale. The underground world of this continent is simply very large, and the history of human exploration of it is relatively short, and the pace of exploration, while sustained and productive, has not yet come close to mapping everything that exists. There is something genuinely exciting about this, something worth celebrating rather than lamenting. We live on a continent that still contains wilderness of extraordinary extent and quality, hidden beneath its surface, waiting to be explored. The tools for exploring it are better than they have ever been. The scientific frameworks for understanding what is found are more sophisticated than they have ever been. The community of people dedicated to this exploration is larger and more capable than it has ever been. The greatest discoveries in North American cave exploration have not all been made. Some of them lie ahead, in passages that no one has yet entered, in chambers that no headlamp has yet illuminated, in underground rivers that have never been observed. The labyrinth extends, patient, quiet, waiting without waiting as stone waits. And somewhere tonight, in a cave system somewhere in North America, water is dripping. It has been dripping for a very long time. It will go on dripping for a very long time more. And each drop adds infinitesimally to the ongoing work of the underground world, dissolving and depositing, shaping and being shaped, building the labyrinth passage by passage, crystal by crystal, in the complete and ancient dark. Let us go back up, not quickly. There is no need to rush. The surface world will be there when we arrive. It has been there all along, a few 100 feet of rock above our heads, going about its business in the light. But let us go slowly, the way the cave deserves. Begin at the deepest point. Imagine the lowest passage of a deep cave system, perhaps one of the active stream passages of Mammoth Cave, where an underground river moves with quiet purpose through a corridor of dark limestone, its surface just slightly luminous in the beam of a headlamp, its sound, a low, soft murmur, the only sound in the absolute quiet of the underground world. Stand here for a moment. The water that is moving past your feet fell as rain somewhere on the surface above. It fell on the forest, on the soil, on the fields, and it seeped downward through 1,000 feet of rock to arrive here. It is carrying dissolved limestone in solution, a calcium carbonate that it has collected from the walls of passages it has moved through. When it reaches the spring where it will eventually emerge into the valley below, it will deposit some of that calcium carbonate as it adjusts to surface conditions, contributing to the tufa deposits and the flowstone that form around cave springs. The water is doing what it has always done. Moving, dissolving, depositing, shaping. The same process that carved the passage you are standing in, extended in both directions through time, the process that carved this passage over the past hundreds of thousands of years, and the process that will continue to carve it. And perhaps new passages beyond it for hundreds of thousands of years more. Geological time is very difficult to hold in the mind. Our lives are measured in decades. Our recorded history spans a few thousand years. The age of any one human civilization is, at most, a few millennia, a moment so brief in geological terms that it does not register on the timescales at which the cave operates. The cave was being carved when our most distant ancestors were still living in ways that left almost no trace in the archaeological record. The cave will still be here, still changing, still growing, still carrying its underground rivers toward their springs, long after everything we have built on the surface of this continent has been erased by time. This is not a frightening thought, or it need not be. It can simply be a clarifying one, a reminder of the scale at which the Earth operates and of the extraordinary privilege of living on a planet that is so old and so complex and so continuously creative. Begin moving upward now. Follow the passage as it rises, gently at first, then more steeply through sections where the ceiling lowers and you must duck, and sections where the passage opens into small chambers where the formations on the walls catch the light and hold it briefly before releasing it back into the dark. The temperature is changing slightly as you rise. Cave temperature in temperate regions corresponds roughly to the mean annual surface temperature above, a stable, year-round condition that represents neither the summer heat nor the winter cold, but the average of both. As you move toward the surface and the cave begins to be influenced by surface air, the temperature will begin to vary more, moving toward whatever the season holds above. Think about water for a moment as you walk. Water is the architect of this entire world. It fell from the sky as rain on ancient continents. It dissolved limestone in the shallow seas where marine organisms accumulated their calcite shells. It carried those dissolved shells downward through fractures in the rock. It carved the passages and chambers of the cave system through which you are moving. It fills the pools and runs in the streams and drips from the ceiling to build the formations on the floor. It circulates through the aquifer and emerges in springs that feed the rivers that carry it back to the sea, where it evaporates and falls as rain again. Water is patient in the way that only things with no will can be patient. It does not decide to carve a passage through rock. It simply responds to gravity and chemistry and the shapes of the spaces it finds itself in. And over time, geological time, the only time that matters in this story, the cumulative effect of that patient, will-less response is the labyrinth through which you are walking. Continue upward. The passage narrows, then opens again. The air begins to move just slightly, a breath of something different from the perfectly still air of the Lechuguilla Cave. This is the cave breathing. Air is moving through the system in response to pressure differences between the cave interior and the atmosphere above, and as you move toward the entrance, you begin to feel it. It is cool and slightly damp, carrying the mineral smell of the cave, a clean, ancient smell, the smell of limestone and still water and long darkness. Think now about the people who have walked this way before you. The Paleo-Indian and archaic and woodland period people who carried cane torches into the darkness 4,000 years ago and moved through passages very much like this one. For purposes we can only partially reconstruct from the evidence they left behind. The Cherokee and Osage and Shawnee and Pueblo peoples who lived alongside these landscapes for centuries and developed relationships with the underground world, relationships of knowledge and meaning and spiritual significance that have been maintained across generations of extraordinary historical disruption. The enslaved man who took a lantern into the unexplored sections of Mammoth Cave in the 1830s and came back with a map. The cave explorers who spent weekends and vacations in difficult, muddy, cold underground passages, adding inch by inch to the growing survey of cave systems whose full extent they knew they would never live to see completely mapped. The scientists who lowered themselves into Lechuguilla Cave in 1986 and found themselves in a world that astonished them. The cave divers who carried tanks of breathing gas into flooded passages in the caves of Florida and returned with knowledge of underground rivers that nobody had previously known existed. The researchers who drilled into stalagmites and read, in the chemistry of their layers, the record of rain and drought and temperature change across hundreds of thousands of years. All of these people were doing the same essential thing. They were paying attention. They were moving carefully through a world that did not make itself easy to understand, and bringing back what they found and adding it to the accumulated knowledge of the community of people who care about this world. The entrance is close now. You can feel it, the air is moving more strongly, and it carries, faintly, the smell of the outside. Soil, living things, something that is not the clean mineral smell of the Lechuguilla Cave. The darkness ahead of you is beginning to change. It is still dark, there is no light source within sight, but somewhere beyond the next bend in the passage, there is a quality of the dark that is slightly different, less absolute, as if the darkness has become aware that it is near its edge. A few more steps, and there it is, a pale oval of grey light at the end of the passage, the cave entrance framing a piece of the surface world, trees perhaps, the grey-blue light of early morning. The sky visible in a small irregular frame of stone, still holding the last of the night. Step through. The air that meets you is different from the air you have been breathing, warmer, richer, full of the biological complexity of the surface world. You can smell the soil and the leaves, and the faint dampness of recent rain. A bird is calling somewhere in the forest, a sound so perfectly normal and so utterly different from the underground silence that it seems for a moment almost startling. The sky above the trees is lightening in the east. Dawn is coming. It is the same dawn we described at the beginning of this journey, the light that swept across the mountains and the forests and the rivers and the plains of North America, the light that revealed a continent of extraordinary beauty. But now, having spent time in the world beneath that continent, the light looks slightly different, more significant, more specific, because now you know that beneath every landscape, the dawn is touching beneath every mountain and forest and desert and plain. The underground world continues in its patient work, the water moving the stone, dissolving and rebuilding the cave ecosystems, going about their extraordinary business, the formations growing their infinitesimal layers, the underground rivers carrying the continent's rainfall toward its springs. The surface world and the underground world are not separate things. They are the same system, operating at different scales and different time scales. The rain that falls on the forest above a cave becomes the underground river that carves the cave passage. The carbon dioxide in the cave air, produced by the decay of organic matter above, makes the water acidic enough to dissolve the limestone. The springs that emerge from cave systems feed the rivers that water the forests that transpire moisture into the atmosphere that falls as rain. Everything is connected. Everything is continuous. The boundary between the underground and the surface is real, but it is permeable. Water and air and life, and even in some cases, light, move across it in both directions. And the boundary between the known and the unknown is real too. But it is also permeable, permeable to curiosity, permeable to patience, permeable to the particular kind of courage that belongs to the underground world, quiet, methodical, sustained, attuned to the specific demands of a place that offers extraordinary rewards to those willing to learn its language. The exploration is ongoing. Tonight, somewhere in North America, a team of cavers is rigging ropes over a pit whose bottom has never been seen. Somewhere, a cave diver is entering a flooded passage that extends beyond the limit of any previous dive. Somewhere, a hydrogeologist is analyzing dye trace results that suggest a connection between a sinking stream and a distant spring. A connection that, if confirmed, will reveal an underground water system of a size that nobody previously suspected. Somewhere, a researcher is drilling a tiny core from a stalagmite and preparing to read in its layers the record of rain and drought from 1,000 years before the first human being stood at the entrance of the cave where it grew. And somewhere, in a passage that no instrument has yet detected, in a chamber that no headlamp has yet illuminated, in a section of underground landscape that exists in the same darkness it has always existed in. Completely indifferent to the question of whether it will ever be discovered, the cave continues, the water drips, the formations grow, the underground river moves, patient, quiet, ancient beyond the reach of imagination. The surface world is beautiful. The mountains and the forests and the rivers and the plains of North America are among the most extraordinary landscapes on Earth, and they deserve the care and attention and wonder that human beings can bring to them. But the underground world is beautiful too. Beautiful in a different way, a quieter, darker, slower, older beauty. The beauty of a world that does not need to be seen to be real, that has been building itself in the dark for longer than our species has existed, that continues its patient work regardless of whether any human being is paying attention. The greatest wilderness of North America may not stretch across its mountains. It may quietly flow beneath them, in the rivers that never see the sun, in the chambers that no map has yet recorded. In the darkness that has been waiting, patient as stone, since before the first light ever touched this continent's surface. The labyrinth goes on, and somewhere, just beyond the edge of everything we know, the passage continues.